This is the second video on Chapter 19, Basis and Dimension. And so what we want to do is we want to focus on these three corollaries. So corollary 209 says that every basis for a vector space has the same number of elements. And if we look at definition 210, that's what the dimension of the vector space is. It's the number of elements in any basis for the vector space. Corollary 210 or 211 says that if you know the dimension of the vector space, then any linearly independent set with that same number of elements is a basis. And then corollary 212 says that if you know what the dimension of the vector space is, then any spanning set with that number of elements is a basis. And so we're going to use these two corollaries, in particular corollary 211, to do parts A and B of example 213 and also example 214. So example 213a asks us, do these three vectors form a basis for R3? Now, we already know that R3 has dimension 3, so all we need to answer is this a spanning set? If it is, we can use corollary 212, and we can also ask, is this set of vectors linearly independent? And if it is, we can use corollary 211. And that's the technique that we'll use for this particular example. We'll make the matrix whose columns are the given vectors. So we have 2, 1, -3, 1, 0, 3, 1, 7. So we make a matrix by taking these vectors as our columns. And we put this matrix in reduced row echelon form. And when we do that, we see that we do have the identity matrix. To save time, I'll just write that as I3. So this is a 3 by 3 identity matrix. Therefore, the columns are linearly independent. Therefore, the columns are linearly independent. That means the vectors are linearly independent, and so by corollary 211 we do have a basis. So the vectors form a basis. By corollary 211. We'll apply the same technique to part B. We have three vectors in R3. These three vectors form a basis if and only if they're linearly independent, also if and only if they're a spanning set. But again, we'll employ corollary 211 and check to see if the three vectors are linearly independent. So we'll use the same technique. We'll make the 3 by 3 matrix whose columns are these three vectors. We'll put the matrix in reduced row echelon form using row operations, and when we do, we have the following matrix. First row is 1, 0, 5, the second row is 1, 0, -4, and the third row is 0, 0, 0. We have 2, not 3 pivots. Since we have fewer than 3 pivots, our columns are linearly dependent. Okay. A basis has to be a linearly independent spanning set. Since these three vectors are linearly dependent, they do not form a basis for R3. And finally, we will look at example 214. In example 214, we are given four matrices in M2 by 2 and asked if they form a basis for the vector space. So our set of vectors, and again, in this vector space, vectors are matrices. So we have a set of vectors that we are given, and we're asked if these vectors form a basis, or if this set is a basis for the vector space of 2 by 2 matrices. Now, from example 205, this implies that the dimension is 4. So we found 4 linearly independent vectors here, so 4 linearly independent matrices that spanned M2 by 2. So we know that the dimension is 4. So the question is, are these 4 vectors in this space linearly independent or not? Okay. So we're going to show that they in fact are. So let's suppose, and we don't necessarily need to know that at this moment, but let's suppose that A times the first matrix plus B times the second matrix plus C times the third matrix So we're going to suppose that we have a linear combination of these 4 vectors that form the 0 vector in this vector space. The 0 vector in this space is the 2 by 2 0 matrix. So let's suppose this is true. Okay. Then we can write this as an equation involving a matrix and a vector. So let's take a 4 by 4 matrix whose columns are these entries in these matrices. So we have 1, 2, 3, 4. 1, negative 1, 2, 3. Negative 4, 0, 5. Oops. 0, 5. And then finally 1, 1, 1, 1. So we've made a matrix whose columns are these entries. And we'll make a vector, A, B, C, D, is equal to 0, 0, 0, 0. So we have this equation, we've rewritten it in terms of a matrix and a vector. Do the multiplication. A plus B minus 4C plus D is 0. That's what we have from the 1, 1 entries of these matrices. A plus B minus 4C plus D is equal to 0. And it's the same for the other 3 entries. We would have 2A minus B plus 0 plus D is equal to 0. We get that from the second row. 2A minus B plus 0 plus D is equal to 0. So the question now is, can this be a non-zero matrix, or a non-zero vector, or does it have to be the zero vector? So do we have a non-zero solution? So we let A be this matrix. Does AX equal to 0 have a non-trivial solution? In other words, does it have a non-zero solution? That's our question. An equivalent way of asking that question is, are the columns of A linearly independent or linearly dependent? So what we do what we did in the previous examples. Let's take A. In the interest of time, I will not rewrite it. And we see that it's reduced row echelon form. Once we use our row operations to put it in reduced row echelon form, we have I4. In other words, the 4x4 identity matrix. And so the answer to the question that we just posed here is no. So by theorem 195, zero is the only solution of AX equal to 0. Since 0 is the only solution, we have A, B, C, D, this vector has to equal the 0 vector, because this vector is a solution to this equation. But 0 is the only solution to this equation, so this vector has to be the 0 vector, which means A equal to B equal to C equal to D equals 0. Therefore, the matrices are linearly independent. Are linearly independent as vectors in M2 by 2. They are linearly independent as vectors in M2 by 2. So we have a linearly independent spanning set. So the set of matrices is in fact a basis. And that concludes the second video of chapter 19, and that includes all the videos of chapter 19.